Okay, so today we're going to work towards an understanding of how electrons are organized inside atoms, and also how chemists actually specify their localization, where they're localized in writing. So, first thing is, what is an atomic orbital? Atomic orbitals come from Schrodinger's wave mechanical model of the atom. So what is an atomic orbital? An atomic orbital is a 3D shape that an electron has a 90% probability to be found in at any given time inside that orbital. Electrons are constantly moving, and we can't precisely predict where they are at any given moment in time, but Schrodinger's equations will give us approximate locations of all the electrons and all the orbitals inside atoms. Now, I said they're 3D shapes, so what do the shapes look like? Well, there's 4 different types of orbitals, and each type other than S has a bunch of suborbitals, as you will see. So atomic orbitals and suborbitals, these individual 3D spaces, can hold a maximum of 2 electrons. So imagine if you're, I don't know, fluorine. Fluorine has 9 electrons. You can tell they're all 9 can't be in an s orbital or in a p orbital. You're going to see there's organization and a certain way the orbitals get filled. So s orbitals do have a shape. They're considered to be spheres. And we're going to consider the nucleus to be at the intersection point of the 3 axes. So a 1s orbital is the smallest. It can hold 2 electrons. A 2s orbital goes around it and kind of surrounds it. Again, it's a 3-dimensional shape. A 3s orbital would go around that, and you're going to see that there, as far as s orbitals are concerned, there's one for every period of the periodic table all the way up to 7. P orbitals are dumbbell shaped. Okay, what do I mean by that? Okay, there's 3 total suborbitals that are called p orbitals. Px, Py, and Pz. As you'll see, they kind of align along the x, y, and z axes in our little graphical picture here. A p orbital total can hold 6 electrons. Each individual suborbital holds 2. So this is when all 3 are stacked. Now I'm going to do a little bit of stuff with balloons to show you how this is organized too in a few minutes. So normally I do this in class, but I got some balloons and I'll try to do it at home. Now, D and F orbitals are even weirder. So there's actually 4 types of orbitals, S, P, D, and F. Each S orbital can only hold 2. There's 3 suborbitals for P. They can hold up to 6. D has 5 suborbitals. Each can hold 2. So D orbitals total can hold 10. And F suborbitals, there's 7 different shapes. And so each of them can hold 2, so there's actually as many as 14 electrons in a given period's F suborbitals. Now, those are the shapes. You don't need to know all of them. You just need to know the S and P orbital shapes. You do need to know that there's 5 D orbitals and 7 F orbitals, and that means Ds can hold 10 electrons and Fs can hold 14. Now, electrons are organized into the different orbitals, and there is a specific way of writing them. That is, writing the locations of all the electrons in any atom can be specified by a chemist knowing how to write these properly. Now, each element has a unique arrangement. Remember, the line spectra for each element is unique. So guess what? They have a unique arrangement of the electrons in these different orbitals, which is one reason why we have unique line spectra for each element. Now, what is an electron configuration? First, it starts with a number. The number signifies the energy level the electron is located in. Now, what that really means, as far as if we're looking at a periodic table, it's the period number, for the most part. The second thing you'll see is a letter indicating the orbital shape, whether it's S, P, or D. We usually, so subscripts are used for suborbitals X, Y, and Z, but when we're actually writing a full electron configuration, we usually just write S, P, D, and F. And as you'll see, what we use are superscripts to indicate the number of electrons in the entire orbital, as opposed to breaking it down into X, Y, and Z for P, or 5 different shapes for D, or 7 different shapes for F. Now, the orbitals will fill in the order on the colored periodic table. Now, everybody, hopefully you printed this colored periodic table as per the instructions. You were asked to have that handy so you could refer to it. So orbitals fill in the order of this colored periodic table from left to right, top to bottom. Now, what does it look like? Here it is. You can see that the first 2 groups, your alkali metals and your alkaline earth metals, they have electrons in this s block, or s orbital. If you go over here to the elements, the last 6 elements of each period, and this is just showing some of the periods, those are all considered to be in the p block. And then if you look in the middle, you notice that there's 10 wide elements. That's the D block, and the F block are those rare earth elements that we don't really deal much with, that are found on the bottom of most periodic tables. Now, keep the thing handy, and we're going to talk about how things are organized. So here's the organization of the first 12 elements. So hydrogen has a 1s1 electron configuration. 1 comes from, guess what? It comes from the period. It's in the first period. S comes from its location. It's found in the S block. And the superscript 1 means it has 1 electron. So when you look here, hydrogen is in the S block. We know that hydrogen has 1 electron, and it's in the first period. So it's 1s1. Now, helium is also found in the first period. Those are the only 2 first period elements. So the electrons in the helium are still in the first period, so they're still in the first energy level. And the only thing we have in the first period is 1s orbital. And so the 2 electrons that are found in the helium are both in the s orbital. So if you go back and look, here's helium. Now you notice we moved it away from the noble gases over here and put it here, just so we could get it in the S block for this analysis. You'll see there's lots of different ways of organizing the periodic table. So helium has 2 electrons. It's in the first energy level. It's in the S block, and it's got 2, so 1s superscript 2. Now, lithium. Okay, lithium has 3 total electrons. So where do the electrons go? Well, the first 2 electrons will go into a 1s orbital. And then the third electron will go into a 2s. And so that third electron, you can see it has a superscript 1. Now let's go back and look what I'm talking about. So 1s1, 1s2, and this one's 1s1 because it's got a smaller s orbital, and then it's got a 2s1 because 1 electron is in the 2s. Guess what beryllium is going to be? It's going to be 1s2, 2s2, because it's got 2 electrons in the second s orbital. So let's take a look. 1s2, 2s2. Boron is the first one that has a electron in a p orbital. So again, reading left to right, just filling in our sequence, 1s2, 2s2, 2p1. Carbon is the next one, 1s2, 2s2, 2p2. Nitrogen is the third one, 1s2, 2s2, 2p3. Now let's go back again and take a quick look. What am I talking about? So let's say you're talking about nitrogen, which is here. Remember, it's got 1, 2, 3, 4, 5, 6, 7 electrons. So you have to specify where all 7 are. 2 of them are in a 1s orbital. That's 1s superscript 2. 2 more are in a 2s orbital. That's 2s superscript 2. And then the next 3, 1, 2, 3, are in a 2p orbital, so it's 2p superscript 3. And that would be the electron configuration of nitrogen. Oxygen, 2p4, fluorine, 2p5, neon is 2p6. Now, neon is a noble gas. And you're going to see this gets really tedious because once we start going down the periodic table, these things get longer and longer and longer. So there is something called noble gas shorthand. The way it works is you can write out the whole configuration piece by piece, or you can take the noble gas from the period above the element, put brackets around it, and then only put the part that's from the period that the element is found. So let's take a look. Where is neon? Neon's at the end of the second period, right? Neon is right here. This is the first period. Here's your second period. There's neon. It's at the very end. So if we want to write an electron configuration for sodium that's really fast, we write the symbol neon inside brackets, and then we put a 3s with a superscript 1. And so guess what? For magnesium, it would be the same thing, brackets, but then it would be 3s2. And if you keep going across, then you'll start getting into the p orbitals again, and then you'll have 3p1 and 3p2 until you fill it. Okay, now moving on to the concept of valence electrons. Valence electrons are the electrons involved in bonding. All right, those are the outermost electrons. Now, valence electrons are also the ones closest to the surface of the atom. You might notice, I'm going to show you a little bit about stacking. The different energy levels all stack on top of each other. So only the outermost electrons, those are the electrons in the highest period that the element is found in, only those electrons in the s and p orbitals there have any chance of bonding. So valence orbitals, electrons correspond to the electrons in the s orbital and the p, x, py, pz suborbitals of the highest energy level where your element is found. That is what period it's found in. Okay, now, for those of you who are, I don't know, much better at math than me, everyone else you can just tune out. But if you really want to see what Schrödinger's equation looks like, it's this. And I could not explain that to you in a million years. If you want to punch in the link, you can go to a site that maybe you can get enough information. If you're really good at calculus, you can probably make a lot more sense of it than I can.